If there's nothing special beyond our horizon, why do galaxy clusters look like they're being pulled by an invisible hand? What's out there? Just more of the cosmic web, or the trace of colliding worlds? We'll go to the edge of what we can see. We'll search for clues in the ancient microwave light. We'll also track how matter moves. By the end, you'll get a straight answer, a rare fluke, or a mark from beyond. We say the universe, but we only ever see a slice of it, like standing on a beach at night and mistaking the moonlit surf for the whole ocean. Light is fast, but not infinite, and time is old, but not eternal. So our view has an edge. It isn't a wall, it's an observable horizon, a limit of contact. Anything beyond it is like a distant lighthouse whose beam simply hasn't reached our shore yet. On the way to us, space itself stretches, the way a sheet of rubber thins when you pull it. A photon loses energy, its wavelength elongates, it slides red and cools, and faraway sources arrive as whispers rather than shouts. Go back far enough and you hit a fog bank the eyes can't see through. The early universe was hot and opaque, a crowd so dense that photons couldn't slip between the shoulders. It isn't empty behind that curtain, we just can't look there directly. Then the fog lifted. As the plasma cooled, light decoupled and began to travel freely, leaving behind what we now see as the cosmic microwave background. An ancient microwave glow, about 3 kelvins, almost featureless, but not quite. In 1992, COBE showed the wrinkles clearly for the first time. In 2003, the Wilkinson microwave probe mapped them in detail. In 2013 and again in 2018, Planck sharpened the picture and cleaned the smudges. Think of that surface as our window pane. Beyond it, for photons, is darkness. But the fingerprints of earlier events are still pressed into the glass. Ahead of us lies the sphere of the observable universe, the farthest region from which light has reached us over roughly 13.8 billion years, because the fabric has stretched while that light was en route. The today distance to that edge is larger than a simple years equal light years count. It runs to tens of billions of light years. Push farther and you meet a different kind of boundary, where recession from expansion matches the speed of light. It's less a locked door than a moving walkway running the wrong way. Signals can step forward, but struggle to ever catch us. These limits explain why the horizon stays silent, even if the universe is busy beyond it, and yet the map still throws curiosities. On the smooth background sits a broad, cool patch, nicknamed the cold spot, a coffee stain that makes you wipe the table twice. There were reports of a coordinated cluster drift on giant scales, the so-called dark flow, written up by Alexander Kashlinsky's group in the late 2000s. Some hints faded under reanalysis, some lingered longer than skeptics liked. Where do rare flukes end and a real story begin? It's the difference between a rumor that evaporates and a pattern that survives the fact check. From here, the road forks in 2 natural ways, even if we're walking the same sky. If the cosmic web beyond the horizon looks like ours, why does our window carry marks at all? If it's different out there, why do many of those marks weaken, not strengthen, as we move from COBE to the Wilkinson microwave probe to Planck? It's like listening to a melody on better speakers and finding that some supposed new instruments were just room echo. The ancient light remains our first clue. Its nearly perfect surface holds ripples precise enough to speak about the shape of space and how large structures grew. In those millions of pixels are the imprints of early processes, and maybe the shadows of things we can't see directly. The way a seismograph records a quake you never felt, where transparency ends, direct sight ends, but the consequences don't. So the observable horizon isn't a dome or the edge of reality. It's the edge of contact in a world where space expands, light ages, and transparency only turns on after a threshold. Everything else stays off screen, but not necessarily without influence. If something beyond the horizon tugs on our web, it should leave a trace, a slight bias in the sky map, a nudge in galaxy motions, a faint asymmetry in the smoothest light we know, the kind of subtle pull you notice when a tightrope quivers even though the acrobat is out of frame. In the early universe, the surface of last scattering isn't poetry, it's plumbing. Picture a neon-bright ballroom, so crowded that every photon keeps shoulder-checking charged particles. Nothing can move in a straight line. About 380,000 years after the beginning, the room cools, partners pair off, electrons with protons in the crowd thins, the fog lifts, the exit doors swing open, and photons finally slip free to cross the floor. They have been traveling ever since. What we see today is that freed light cooled down to a faint microwave afterglow. About 3 kelvins, almost smooth, with ripples only tens of microkelvins deep. On a map, they look like wrinkles pressed into a bedsheet. They are not static. They are the fossil breeze lines from early density waves, the way sand holds the pattern of a wind that has already passed. This is why the background is our window pane. It doesn't show stars and galaxies themselves, it shows their seeds pressed into the glass. In 1992, CMB brought those wrinkles into focus for the first time, like switching on a desk lamp over an old photograph. In 2003, the Wilkinson microwave probe drew them in finer strokes. In 2013, and again in 2018, Planck cleaned the lens and tightened the frame. The image got sharper, but the meaning stayed put. We are looking at the first free light. It is called a horizon because you can't see earlier than clear glass. Before decoupling, the medium was opaque, like trying to spot a lighthouse through boiling milk. And even this window has thickness. The transition from foggy to clear took a little while, so the tiniest features blur at the edges, the way a fast hand smears in a long exposure. There is a second ruler hidden in the picture, the sound horizon. In that young plasma, pressure waves rang outward like ripples in a heated drum. The farthest a wave could travel before the fog lifted sets a characteristic angle on the sky, about 1 degree. At that scale, the background hits its first acoustic peak. Later, we hear the same beat in galaxy surveys as baryon acoustic oscillations, a tape measure laid across the cosmos. The window isn't just a picture, it's a yardstick. To read the physics cleanly, we scrub the glass like a conservator, restoring a painting. We remove the dipole that comes from our own motion through the glow. We mask the bright plane of the Milky Way. We compare multiple frequencies to peel away dust and synchrotron, like viewing the canvas under different lamps. Then comes the hard part. If a feature is real, it survives new masks, new methods, new colors of light. If it lives through that, we keep it. If it doesn't, we let it go. Even on this smooth field, a few oddities catch the eye. The cold spot in the southern sky is a broad, cool patch, like a coffee ring that makes you wipe the table twice. Some tie it to a big underdense void along our line of sight. Others call it a rare coin toss. With better calibration, several temptations faded. A few linger at the edge of significance. On the largest angles, talk of a low quadrupole and aligned low multipoles, the headline axis of evil, softened under stronger data, as if a rumored whisper quieted when the room got brighter. What makes the wrinkles in the first place depends on how ordinary they look. For the usual pattern, it is inside work. Acoustic waves, gravity wells, and the Sachs-Wolf effect, leaving cooler smudges where wells are deeper, the way a marble slows in a bowl. When a patch looks strange, we test outside stories. A scar from a distant collision, a thin thread from an extended defect. But any outside script has to pass simple trials. Survive the leap from the Wilkinson microwave probe to Planck, remain after harsher cleaning, and match across frequencies. If it passes, we have a clue. If not, it was a shadow puppet on the wall. There is also a common sense calibration baked in. The sound horizon pins the key angular scale, letting us test the shape of space, while the heights of the acoustic peaks tell us how much matter there is and how deep the gravity wells were, like reading a landscape from the spacing and size of its dunes. Against that baseline, real asymmetries stand out quickly. That is why this surface is both window and defect detector. If anything beyond our horizon left even a faint mark, the sharpest place to catch it is here, in millions of pixels of ancient light. From this window, the logic naturally steps to geometry and early smoothing. On the largest scales, space looks nearly flat, as if some early steamroller passed once to iron the wrinkles. A brief growth spurt can explain that. The next move is to connect the view from this glass to flatness itself, and to the case for a burst of rapid expansion near the beginning. The big-scale map of space behaves as if it is flat. You can see it in the ancient light. The strongest ring of its ripples sits at about 1 degree. That is exactly what almost Euclidean geometry predicts. In the early 1990s, the satellite CMB first hinted at this order. In 2003, the Wilkinson microwave probe made it clear. In 2013, and then again in 2018, Planck locked it in with very small errors. Independent rulers agree. Baryon acoustic oscillations in galaxy maps and Type 1a supernova distances. Both say the overall curvature is consistent with zero within the uncertainties. Where does this flatness come from? From cosmological inflation, a short, extremely fast early growth of space. The core idea was set out by Alan Guth in the early 1980s. Andre Linde, Andreas Albrecht, and Paul Steinhardt developed rolling field versions. A bit earlier, Alexander Starobinsky showed how an equivalent scalar field naturally speeds up space in a modified curvature model. The plain language picture: if space balloons very quickly, any initial bends get ironed out. A hilly surface becomes a near-level plane. Regions that later drift far beyond mutual contact first had time to even out their properties. This also explains a famous puzzle. Opposite sides of the sky have almost the same temperature even though there was no time for light to travel between them. With an early sprint, neighboring patches equalize first, then race apart beyond each other's horizon. In map terms, you get an almost scale-invariant spectrum of ripples, waves of different sizes with similar strength and a slight tilt downward. The Wilkinson microwave probe saw this tilt clearly. Planck confirmed it. Not noise, not an artifact, a real physical slope. Checks go beyond temperature. The polarization of the ancient light carries the same story. The modest but solid A polarization mode supports the acoustic picture. The search for B polarization mode, the swirl pattern from primordial gravitational waves, became a field of its own. In 2014, the background imaging of cosmic extragalactic polarization, pronounced BICEP, reported a possible signal. A joint analysis with Planck showed that galactic dust was underestimated. Later BICEP and the Keck array tightened the upper limit. The tensor contribution is at most a few percent. Important point: inflation does not have to shout in gravitational waves. Quiet bimodes narrow the options but do not kill the mechanism. Geometry meets late-time expansion too. In 1998, the teams of Saul Perlmutter, Brian Schmidt, and Adam Rees, using Type 1a supernovae, discovered that expansion is accelerating. Combine those distances with Planck and with baryon acoustic oscillations, and the best fit comes with almost zero curvature. Geometry and dynamics line up. On billion light-year scales, space looks flat, and the history of expansion needs a component, like a cosmological constant. What does that suggest about the beyond? If the early sprint flattened bends and evened out temperatures over huge swaths, then beyond our visible edge, the same fabric likely continues. Rare quirks on the map, the cold spot, or faint hints of alignment on very large angles should behave like rare coincidences or subtleties of foreground cleaning. Still, the door is not shut. Inflation can also leave rare marks, such as collisions of bubbles or thin defects. If anything like that happened, the imprint should show up where the inflation ruler is strictest, around 1 degree in temperature, in matching E polarization, and on the cleanest parts of the sky where dust barely whispers. Flat geometry is not a slogan. It is a quantitative result. It comes from angular scales in the ancient light map, from the relative heights of the acoustic rings, and from independent galaxy and supernova statistics. This flatness has a price. It needs an early sprint or an equivalent mechanism. Today, cosmological inflation remains the simplest bridge from a near-uniform map to a near-flat geometry, with names, dates, and data in the archives of CMB, the Wilkinson Microwave Probe, and Planck. Large-scale structure is not a random scatter of dots. It is a web of filaments, voids, and flows, the fabric of space showing which way matter drifts. The Sloan Digital Sky Survey, in the early 2000s, mapped a network stretching hundreds of millions of light-years. The 2-degree Field Galaxy Redshift Survey and the 6-degree Field Galaxy Survey added depth. Redshifts turned a flat map into a 3-dimensional picture. Some regions earned names because their mass stands out: the Great Attractor, the Shapley Concentration, Perseus Pisces. In 2014, Brent Tully and colleagues named our home supercluster Laniakea Immense Skies. In 2017, Yehuda Hoffman described the Dipole Repeller, a low-density region that seems to push us outward. Pull and push make one coherent pattern. How do we read motion? First, we compare the ideal Hubble flow galaxies drifting apart with expansion to what each galaxy actually does. The difference is a peculiar velocity, the galaxy's own speed on top of expansion. We estimate distances with standard candles and standard rulers. Type 1a supernovae set distances by their brightness. Spiral galaxies follow the Tully-Fisher relation. Elliptical galaxies line up on the fundamental plane. Redshift carries the expansion piece. Any offset above or below the ideal line is a gravity clue along our line of sight. Stack many such clues, and you can build a velocity field and look for a shared drift of huge volumes, the bulk flow. Around the turn of the 2000s, papers reported a large bulk drift on scales of hundreds of millions of light-years. In 2009, Richard Watkins, Hume Feldman, and Michael Hudson reported a significant coherent speed on scales of about 100 million light-years. In parallel came another probe, the kinetic Sunyaev-Zeldovich effect. Hot gas in clusters slightly shifts the temperature of the cosmic microwave background when a cluster moves. In 2008 and later, Alexander Kishlinsky and co-authors reported a possible dark flow, many clusters moving in roughly one direction, as if a massive tug lay beyond the visible window. Better maps and cross-checks followed. In 2013, Planck released its first results, with refinements after. Using hundreds of clusters, the average kinetic signal pointing one way did not appear. The data were consistent with near-zero bulk speed on the largest scales in the standard picture. In the south, the 6-degree Field Galaxy Survey reconstructed the peculiar velocity field and showed how local flows arise from a mix of massive knots and nearby voids. No distant hidden driver required. The Cosmic Flows projects assembled 3-dimensional velocity maps for tens of thousands of galaxies and showed how the Shapley concentration and other hubs add up to set our local drift. The picture is two-layered. On scales of tens of millions of light-years, nearby mass rules, the Great Attractor, the strands toward Perseus Pisces, the rims of voids. On scales of hundreds of millions of light-years, the net drift weakens and matches what you expect from an almost flat geometry with cold dark matter. The idea of a faraway outside tow truck faces skepticism. New maps do not confirm a large effect. Yet the door is not shut. Sensitivity keeps improving, and tiny signals at the edge of statistics demand care. Void is a driver too. The dipole repeller shows how a low-density region can push matter in a way comparable to the pull from a massive supercluster. Early and late maps must also fit together. If a very dense region beyond the horizon were tugging on us, you would not only see a drift and peculiar velocities, you would also expect a matching imprint in the ancient light on the largest angles and in cross-correlation with cluster locations. That is why the cosmic microwave background and redshift catalogs work best as a pair. The temperature wrinkles set the initial conditions. The flows show how they grew. Near the sensitivity limit, weak spots remain. Dust masks hide parts of the sky. Small calibration, offsets between frequency channels, and systematics in distance catalogs can imitate or hide a small effect. So every new release is not just a number in kilometers per second. It is also a checklist of cross-checks, independent samples, alternate methods, and reruns by other teams. What does this say about the far side of the horizon? If the same cosmic fabric continues, bulk flows on very large scales should be modest and fade as you average over larger volumes. If there is an exception, an unusually massive knot or a rare asymmetry in the initial conditions, its shadow must show up in two places at once, on the map of ancient light and in the vector field of galaxy speeds. That is the power of bulk flow as evidence. It is a test written not in one patch of sky, but in the motion of the whole visible volume. On the map of ancient light, there is a stubborn oddity, a cold spot on the southern sky. Its temperature is lower than its surroundings. The contrast is tens of microkelvins. With a small filter, it looks like a patch tens of arc-minutes wide. After smoothing, it grows to several degrees. The first solid reports came in 2004. A Mexican hat wavelet picked out a deep minimum in the Wilkinson microwave probe data. In 2013, Planck confirmed a local dip in the same direction, near the constellation Eridanus. The cold minimum is real. The fight is about how rare it is. One simple path says, a rare chance on a very large map. In the standard picture, the ancient light behaves like an almost random field with a known grain. Deep dips are allowed. If you tune the filter scale, slide the search window, and test many times, the formal significance drops. With those corrections, the cold spot often lands near the edge of what is still allowed. Better calibration and stricter dust masks make the map cleaner. The minimum remains, but without a model-breaking headline. Another path runs along our line of sight. If a super void, a very underdense region hundreds of millions of light-years across, sits on the way, its changing gravity can slightly cool the ancient light. That is the integrated Sachs-Wolf effect. In 2015, infrared and optical surveys, Wide-Field Infrared Survey Explorer, 2-micron all-sky survey, and Pan-STARRS mapped a sparse region in that direction at low redshift. Calculations show the void does make a cool imprint, but usually weaker than the full depth of the cold spot. Part void, part statistics. A third idea once had traction, a texture, a relic of an early universe phase change. It predicts a specific temperature profile and a likely signature in polarization. As the maps improved, especially with Planck, the allowed share of such textures shrank. You can fit the profile, but then the sky should show more similar cases. It shows very few. Polarization is the independent test. If the minimum was seated at the surface of last scattering, there should be a specific E-mode pattern around the center. If the minimum formed later because of a void, that link is weaker on the needed angular scales. Polarization maps are still noisy, yet one thing is already clear. The strong primary signature is not there. The door is not shut, but it is mostly closed. Data cleaning matters as much as physics. First, we remove the dipole, the trace of the solar system's motion through the ancient light. Then we mask the galactic plane, where dust and synchrotron dominate. Then we compare frequency channels to subtract the foreground without throwing away real sky signal. From Wilkinson microwave probe to Planck, masks and methods got tougher. The cold spot stayed, the drama cooled down. Galaxy maps toward Eridanus add detail. The density falls over large distances and then returns to average, as a healthy large-scale structure should. In stacking, piling the ancient light map onto the positions of many independent voids, the integrated Sachs-Wolf effect shows up as a small average cooling. It matches the standard model, but it rarely reaches the depth of the coldest part of this spot. That sets limits on a pure astronomical cause and supports a mixed picture, some void, some rarity. So the working picture is plain. The temperature dip is real. The super void explains part of it. The rest looks like a rare fluctuation. Primary defects are tightly constrained by the data, the large sky area, and independent checks favor the ordinary explanation. while the spot's stability across missions keeps the tempting idea of one source alive. What does this say about the far side of the horizon? If the same fabric continues, the cold spot is a rare fold in an otherwise smooth cloth. If there is an exception beyond our horizon, its shadow must appear in two places at once, on the ancient light map and in the matter pattern along the same line of sight. While temperature and polarization keep gaining precision, the cold spot stays a stress test of the ordinary continuation story, and a reminder that even the smoothest background can hide a patch where rarity looks like a plot. Beyond our observable horizon, the same fabric likely continues, the same laws, the same web of filaments and voids. If that is true, the ancient microwave light and the later rulers of distance should agree. Do they? Yes, almost everywhere we look. Start with the ancient microwave light. Its main ring of sound sits at about 1 degree. That angle points to an almost flat geometry. In the early 1990s, COBE revealed tiny micro-Kelvin wrinkles. In 2003, the Wilkinson microwave probe mapped their scale and showed the tilt of the pattern, just below 1. In 2013 and 2018, Planck tightened the errors to very small values. The picture stayed smooth, with a fine relief that a simple version of explanation describes well. Next comes the ruler in the galaxy maps. Baryon acoustic oscillations repeat the very same scale we see in the ancient light. In 2005, the Sloan Digital Sky Survey and the 2-degree field galaxy redshift survey pinned that scale down as a stable yardstick. On the sky it was an angle. In 3-dimensional galaxy maps, it became a length, handy, repeatable, checkable. Now add the supernovae. In 1998, the teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees showed accelerating expansion using Type 1a supernovae. When you combine their distances with the Planck maps and with baryon acoustic oscillations, the best fit comes with almost zero curvature. Space looks flat, and the expansion history wants something like a cosmological constant. Put the language on the table. The package is called Lambda Cold Dark Matter, Lambda CDM, meaning almost flat geometry. Cold dark matter drives structure growth, and dark energy powers the acceleration. No hidden tractor beyond the visible edge is required. If the same fabric continues past the horizon, our rulers should agree with each other. They do. Polarization adds an independent check. The E mode records scattering at the dawn of transparency and backs up the acoustic story. The hunt for B modes, the curls from primordial gravitational waves, moves carefully. In 2014, the background imaging of cosmic extragalactic polarization team, set as BICEP, reported a possible signal. A joint study with Planck showed that galactic dust was underestimated. Later, BICEP and the Keck array set a tighter upper limit on the tensor signal. Quiet B modes do not break the picture. They simply narrow the allowed room for the early rush. The late-time universe plays the same tune. The Baryon Oscillation Spectroscopic Survey and the Extended Baryon Oscillation Spectroscopic Survey build 3-dimensional slices where the acoustic ruler appears again. The Dark Energy Survey and the Kilo Degree Survey measure weak gravitational lensing, tiny shapeshifts of distant galaxies, and recover the gravity field that grows structure without distant unseen tractors. The Cosmic Flows projects collect peculiar velocities from Type 1a supernovae, from the Tully-Fisher relation in spiral galaxies, and from the fundamental plane in ellipticals. Local flows add up from known mass knots, like the Shapley concentration and the Great Attractor, plus nearby voids. On scales of hundreds of megaparsecs, the net drift weakens. Exactly what you expect if the same fabric continues beyond the horizon. What about the oddities? The cold spot toward the constellation Eridanus is a real temperature dip. Galaxy catalogs along that line of sight do show a low-density region, hundreds of millions of light-years across. The integrated Sachs-Wolf effect gives a cooling with the right shape, but often with too small an amplitude. The rest can be a rare fluctuation on a huge map, especially after you fairly account for searching everywhere. Hints of aligned large angle patterns fade when you use strict dust masks and alternative cleanups. Reports of a dark flow from the kinetic Synyav-Zeldovich effect move toward consistency with zero once Planck stacks hundreds of clusters, while reconstructions from the 6-degree field galaxy survey explain local speeds with known mass. There is also a quiet but sharp test: repeated circles on the sky. If space were small and closed, the ancient light would show matching rings. Dedicated searches in the Planck maps do not find robust pairs. The simple reading is this: space is either very large or effectively infinite for our purposes. In both cases, the familiar web keeps going beyond what we can see. The forecasts are not about fireworks. On future maps, cosmic microwave, background stage 4, often said as CMBS4, and Lightbird, the spectral tilt, should stay the same, while the upper limits on B modes should get tighter. The Nancy Grace Roman Space Telescope and the Rubin Observatory will sharpen the acoustic ruler and shave more uncertainty off the geometry. If the same fabric continues past the horizon, each new data release will make the world look even smoother, and the exceptions even rarer. So the conclusion is calm. Beyond the visible edge, the same fabric likely continues. Gravity gathers the filaments. Voids expand a bit faster than average regions. The ancient light stays almost even. Rare folds look like rare stories, not new laws. That is what beyond the horizon, the same means here. Not boredom, but stability. The same everywhere idea rests on a calm, even sky in all directions. The argument starts where the very largest angles on the map of the cosmic microwave background refuse to behave. First clue: the cold spot. In 2004, the Wilkinson microwave probe flagged a deep temperature minimum using a Mexican hat filter. In 2013, Planck confirmed the dip, but lowered how exceptional it looked. The spot did not vanish. The drama simply got quieter. Second clue: very large angle patterns. People discussed a weak low-order signal in an alignment nicknamed by journalists the axis of evil. Planck tightened dust masks, improved calibration, and ate away part of the effect. What remains sits on the edge of significance. Third clue: too little correlation on the very largest angles, where you might expect a bit more temperature similarity. The map stays silent. Each item alone can be a rare fluctuation. Together, they are a reason to double-check. The double-check starts with simple choices. Where exactly is the clean dust boundary? Make the mask a little wider and the significance drops. Make it narrower and it rises. Frequency cleaning is touchy too. Subtract dust too hard and you carve out real sky signal. Go too soft and you leave a tail of galactic emission that can mimic cosmology on huge angles. Add in the instrument details, how the telescope scanned the sky, and the exact beam shape. On giant angular scales, these things matter. The late-time universe adds its own voice. In the late 2000s, Alexander Kashlinsky and colleagues reported a dark flow, a common drift of hundreds of clusters, via the kinetic Synyav-Zeldovich effect. If a cluster is moving, its hot gas shifts the microwave temperature a little. In 2013 and later, Planck stacked hundreds of clusters and drove the effect toward consistency with zero. The method is sensitive to which clusters you pick and how you calibrate the temperature maps. Skepticism is healthy. Care is mandatory. Polarization is an independent witness. The letter E mode supports the acoustic picture and the overall smoothness. The letter B mode hunts for curls from primordial gravitational waves. In 2014, the background imaging of Cosmic Extragalactic Polarization Team, often said as BICEP, announced a possible signal. A joint study with Planck showed that galactic dust had been underestimated. Later, BICEP and the Keck array set tighter upper limits for the same everywhere version. This is a useful quiet inflation does not have to be loud. Two simple checks guide the verdict. First, a real feature should weaken when you go from the Wilkinson microwave probe to Planck, when you tighten the dust masks, and when you switch cleaning methods. Second, any hint of outside influence should show up in two places at once, On the temperature map of the ancient light and in late-time data, either the field of galaxy motions or the galaxy distribution itself, where both checks are passed, the sky acts predictably. Where precision is still thin, a narrow strip of unknown remains. New measurements will close that gap. We look in three places: temperature, polarization, and late-time structure. A real clue has to show up in more than one of them and survive tougher cleaning. Start with circles. If two inflation bubbles collided, they should leave a round mark, a circle, or a soft disk with smooth brightness from center to edge. In the early 2000s, teams searched the Wilkinson microwave probe maps with Bayesian scans. In 2011, they reported medium candidates. Planck brought cleaner data in 2013, and after, most of those circles faded. Dust cleaning and different filters removed the shapes. Simple rule: if the circle is real, the letter E polarization must trace the rim the way physics predicts. No E mode on the edge, then the circle is likely processing. What about series of rings? Repeated hits would draw concentric circles. Planck rechecked with matched circle searches. Robust pairs did not survive changes of masks and frequencies. If a series stays under stricter cuts, we keep it. If it disappears, it was the method, not the sky. Now cosmic strings. Picture a one-dimensional defect. It leaves a step in temperature along a narrow line, the Kaiser-Stebbins effect. People run edge finders on the cosmic microwave background and apply the same selection rules to many sky patches. A stable grid of cuts did not appear. The string tension is pushed down to a few times 10 to the -7th. Radio helps. Pulsar timing arrays, the European Pulsar Timing Array, and the North American Nanohertz Observatory for Gravitational Waves limit the stochastic background from loops and sharp cusps. A lone line on a map is only a hint. We also need nearly undistorted lens doubles along that same path, or the right kind of gravitational wave background. Without that, it looks like foreground or an algorithmic edge. Short-lived textures tell a different story. They can make a single cell-like spot with a specific temperature profile. In the late 2000s, the big southern cold region could fit that shape for some settings. Planck narrowed what is allowed and added a clear demand. A primary origin must carry a predictable letter E pattern. That pattern is not seen at the needed level, so the idea slides back to a rare fluctuation or to a late line-of-sight effect. Late structure can cool the map a little. When photons cross a huge underdense region, a supervoid, the changing gravitational potential makes them leave slightly poorer. That is the integrated Sachs-Wolf effect. If you stack the microwave map on many voids and superclusters, you get an average cooling of a few microkelvin that matches the standard picture. Single cases rarely reach tens of microkelvin, so a void can help, but it rarely explains the deepest cold spot alone. If cooling is large, optical and infrared surveys along the same line must show a clear drop in galaxy density. If not, temperature goes back to being a fluctuation of the early field. Each channel has a job. Temperature sets the shape. Polarization tells the origin, laid down at the surface of last scattering or added later along the way to us. Redshift catalogs show where mass and emptiness sit on the sight line. Pulsar timing adds an independent clock for the gravitational wave background. Weak lensing in optical surveys and in Planck lensing checks. If the gravitational potential field matches the mass you would need, a single hint is a shadow. Matching shapes across channels is evidence. Where are we today? Most circle claims weaken with stricter masks or different filters. Linear cuts do not form a convincing network. The allowed string tension is down to a few times 10 to the -7th. Polarization backs the acoustic story and does not require collisions. Late-time surveys, the Sloan Digital Sky Survey, the Dark Energy Survey, and the Kilo Degree Survey, find voids in nodes big enough to explain the average stacking signal, but not enough to carry the deepest single cold spots. What would flip the story? On next-gen maps, Cosmic Microwave Background Stage 4 and Light Bird A true collision circle must come with the correct letter E pattern along its edge. In Nancy Grace Roman Space Telescope and Rubin Observatory data, a void on the way to us must line up with a cooling of the right sign. The European Pulsar Timing Array and the North American Nanohertz Observatory for Gravitational Waves will keep shrinking room for strings. If a mark from beyond is real, it will survive masks, frequencies, and new instruments, and appear at the same time in temperature, in polarization, and in independent catalogs. If it fades, it was a rare fluctuation, not a message from the other side. Marks from beyond only count if they show up cleanly here. A circle on the temperature map must carry the right letter E rim. Without that polarization, cleaning can fake a perfect ring. In the early 2000s, teams scanned the Wilkinson microwave probe maps. In 2011, they reported medium-strength circle candidates. After Planck in 2013, stricter dust masks cut them down. The shapes sometimes stayed, but the letter E rim did not. Cosmic strings would leave a sharp temperature step across a thin line. That is the Kaiser-Stebbins effect in plain words. Edge finders do spot lines, but no stable sky-wide network appears. Planck pushed string tension below a few times 10 to the -7th. Nearly undistorted lens doubles along a straight string are also rare. Pulsar timing arrays see a nanohertz hum that fits black hole binaries. Cosmic textures would make one cell-like spot with a set profile. They also require a matching letter E pattern around it. The big southern cold region once looked compatible for some settings. Planck narrowed the options and raised the bar on polarization. No matching pattern, no primary texture story. Under dense regions cool the map gently along the line of sight. That is the integrated Sachs-Wolf effect. Stacking many voids gives only a few microkelvin on average. Single cases rarely reach tens of microkelvin on their own. If cooling is strong, galaxy counts must drop along the same line. 2-micron all-sky survey, wide-field infrared survey explorer, and pan-stars should show it. If they do not, the dip is likely an early field fluctuation. Here is the state of play on today's maps. Wilkinson-era circles lose power on Planck and lack the letter E rim. String-like cuts lack weak lensing partners and fail radio constraints. For the cold spot, the density drop is smaller than the full dip. Large angle polarization is still noisy, with no clear temperature match. What counts as evidence is simple. A collision circle survives new masks and methods, and shows the right letter E along its edge. A string-like line comes with weak lensing on the same track, and stays within pulsar timing limits. Strong late-time cooling lines up with a real galaxy deficit, with the correct Sachs-Wolf sign. Until then, these marks are only shadows. Real evidence must appear in several channels at the same time. It must also survive new instruments and new skies. From Wilkinson microwave probe to Planck to cosmic microwave background stage, 4 and Lightbird, from Roman Space Telescope and Rubin Observatory to pulsar timing arrays. If a sign is real, it will live through all of that. If it fades, it was never a body, just a trace. Ancient microwave temperature is our first mirror. COBE in the early 1990s revealed microkelvin wrinkles across space. The Wilkinson microwave probe in 2003 refined angles and spectral tilt. Planck in 2013 and 2018 cut errors in dust. On this map, we hunt soft circles and disks from bubble collisions. We also hunt thin temperature steps expected from moving cosmic strings. Textures would appear as single cell-like spots with a set profile. Temperature alone is not enough. We also need polarization there. Along a circle's rim, we expect the right letter E pattern. For late-time voids, that link is weaker by design. Planck's lensing map reconstructs the gravitational potential behind the light. It checks whether the implied mass matches the observed background distortions. Late structure is our second mirror. Sloan Digital Sky Survey and its baryon oscillation programs map 3 dimensions. Baryon acoustic oscillations give a reliable distance ruler across cosmic time. Dark Energy Survey, Kilodegree Survey, and hypersuprime cam measure weak lensing. They recover potential maps without converting light directly into distances. If a temperature dip comes from a void, catalogs must show a density hole. Weak lensing on that line should also reveal a mass deficit. Matter motion is our third mirror. Peculiar velocities come from Type 1a standard candles and galaxy scaling laws. Spirals use the Tully-Fisher relation. Ellipticals use the fundamental plane. Cosmic flows and 6-degree field galaxy survey build three-dimensional velocity fields. They compare flows with poles from Shapley, Perseus Pisces, and the Great Attractor. They also include pushes from low-density regions like the dipole repeller. Too large bulk flow over hundreds of megaparsecs needs extra mass beyond view. Moderate flow supports the same beyond the horizon. Working picture. The changing potential ties these mirrors together. The integrated Sachs-Wolf effect cools or warms light along the path. 2-micron, all-sky survey, wide-field infrared survey, Explorer and Pan-STARRS map structures. Stacking many voids and clusters yields an average few microkelvin signal. That average matches the standard picture without exotic additions. Extreme cases must also show a real density dip and cleaning stability. String searches run in 3 windows at once. Temperature maps use edge detectors to find long step-like cuts. Optical images would show nearly undistorted lens doubles along a straight thread. Radio timing arrays test the nanohertz gravitational wave background for string hum. European pulsar timing array and North American nanohertz observatory set tight limits. Allowed string tension is a few times 10 to the -7th. The shape of space gets a separate test using matched sky circles. A small closed space would show repeated circles in different directions. Planck finds no robust pairs across masks and frequencies, pushing that scale large. Galaxy clusters link back through Sunyaev-Zeldovich effects. Thermal measurements trace hot gas. Kinetic measurements trace cluster motion. Planck Atacama Cosmology Telescope and South Pole Telescope see no big average drift. Large-scale velocities remain modest on the widest scales. A trustworthy signature survives masks, frequencies, and instruments. From the Wilkinson microwave probe to Planck to cosmic microwave background stage 4, from today's optical surveys to LightBird and future timing arrays. It must also appear in several independent channels at the same time. Only then does a hint stop being a shadow and become evidence. We treat each hypothesis like a different map app. Each app has settings, or knobs, you can turn. First we set fair, starting ranges for those knobs, then we ask how well each version matches real data. After seeing the data, the odds update in a simple way. If most settings work, that version gains more weight. If only a tiny slice works, the weight falls away. That is Occam's razor in practice, not a slogan. The baseline picture is Lambda Cold Dark Matter. Pronounce it Lambda CDM. Few parameters, clear predictions, broad room to match. The sky looks almost flat at degree scale features. The Wilkinson microwave probe showed the spectral tilt. Planck tightened errors and cleaned out galactic dust. Baryon acoustic oscillations measured the same distances. Simple wins because much of its allowed space fits. Now the alternatives and their price for complexity. A cosmic texture needs size, depth, center, and polarization. Temperature can mimic it, but letter E is missing. Most allowed settings do not improve the global fit. Cosmic strings should cut sharp steps across the map. We do not see a stable web of such edges. Weak lensing pairs along straight strings are very rare. Pulsar timing arrays hear a background favoring black hole binaries. That squeezes the string tension to a tiny window. Bubble collisions should leave circles with proper polarization rims. Early candidates faded under stricter Planck dust masks, with wide ranges for radius and brightness. Few settings help. The baseline model keeps the higher overall support. Even when complexity is low, wins are scarce. Matched circles would reveal a small closed topology. Planck found no robust pairs across masks and frequencies, so space looks larger than our window would require. This is not armchair theory, it is audited work. Planck publishes likelihoods that weigh all frequency channels. Bayesian estimators compute total support with explicit priors. Sloan dark energy and kilo-degree add mass maps. Pulsar timing arrays bound the nanohertz gravitational background. Together they change not just means but model odds. Think of it like tuning a radio in a storm. A real station comes through on many dials at once. A fake signal vanishes when you change the tuner. Right now, the baseline picture fits wide and well. Space looks nearly flat, by several independent rulers. Marks from beyond remain possible, but they are rare. To take the lead, they must line up everywhere. Temperature, polarization, and late-time matter. Maps must agree. They must also survive stricter cleaning and new instruments. When that happens, the odds will finally swing their way. Imagine filming a night skyline through a window. If the glass is dusty, lights grow ghostly halos. Cosmic maps behave the same way, under dirt and glare. Before arguing about signals from beyond, we check the camera. Calibration is our focus, and white balance for the cosmos. We match each detector's thermometer so channels read the same. We scrub scan stripes like scratches on old movie film. One wrong slider, and a perfect circle becomes a filter stamp. Next comes where we choose to look on the sky. Hunting wonders only in noisy places will spawn many wonders. It is like flipping frames until a coin hits 10 heads. A fair test is simple. Change scale, patch, and cleaning. A real mark holds steady. Lucky noise fades and vanishes. Data cleaning walks a razor-thin edge every time. Clean too hard, and you shave off real cosmic signal. Clean too soft, and dust impersonates deep space physics. So we repeat the job in several independent ways. Different filter, different frequency, different mask for dirty regions. If the shape survives, the conversation continues with confidence. If it dances with each setting, processing is fooling us. The best defense against self-deception is cross-confirmation. See a temperature dip? Matter maps must show a density drop. Weak gravitational lensing should show shapes pulling outward accordingly. Find a clean circle? Letter E, polarization must trace its rim. Think you see a straight cut from a cosmic string? Then look for nearly undistorted double images along that line. Also listen for the right gravitational wave background in radio. A lonely shadow is still a shadow. Matches make evidence. To avoid drowning in pretty pictures, we keep a scaffold. State the question in one line. No poetry attached. Name 2 competing versions and mark their weak points. Pick a single if, then test that could break them. Say what counts as confirmation and what counts as failure. Only then do we stare at plots and sky maps. The ending is boring, and that is its strength. We do not believe silhouettes. We clean the window. We retune the camera, shoot again, and compare other maps. If a mark passes every dull step, it becomes a story. If not, it is a coincidence that happened to catch our eye. Who speaks first? We're hunting for traces from beyond the horizon. But the interrogation happens here. Think of it as a crime lab, with multiple sensors pointed at the same scene. The temperature of the ancient light, its polarization, the stretched shapes of far-off galaxies, the low hum of gravitational waves. If out there is different in any meaningful way, the fingerprint shouldn't appear in one place. It should repeat across several surfaces at once. Start with the background glow. TMBS4 will examine the sky more finely than anything before it, trying to catch the faint B mode curls or compress their allowed space to almost nothing. It's a stress test for early cosmic acceleration and any loud origin stories. Lightbird adds big angle precision from space, like lifting the whole window pane instead of peeking through a keyhole, so we can separate the true cosmic pattern from the dust of our own galaxy. If circles from colliding bubbles are real, the correct E mode must trace their rims like frost around a glass. If it doesn't, that pattern is an artifact of filtering, not a chapter of history. Polarization isn't just a picture. It tells you the time and the culprit. We already burned ourselves on dust once in early B mode. Claim from the background imaging of cosmic extragalactic polarization experiment had to be revised after cross-checks. The rule is stricter now, like two-factor authentication for the cosmos. If temperature shows a shape, polarization must produce its twin. Only then does a silhouette become evidence. Shift to the late universe. The Rubin Observatory, formerly LSST, will re-image roughly half the sky every few nights and measure weak lensing the tiniest stretches in galaxy shapes caused by mass along the line of sight. It's a relief map of gravity and depth. You don't see the mountains, but you feel the ridges with your fingertips. If a genuine void sits along the path to the cold spot, Rubin should catch a systematic outward tug in the shapes. If it doesn't, that temperature dip slides back toward the rare Fluke bin. Euclid and the Roman Space Telescope supply the yardsticks baryon acoustic oscillations and precise redshifts. Picture mile markers down a foggy highway. With them you see not only that the road stretches, but by how much and exactly where. That's how you corner contradictions. Temperature whispers, "There's a dip here," while the catalogs reply no dip, or the other way around. When both agree, the case gets louder. There's a speed map too. Type Ia supernovae give distances. From them we infer peculiar velocities. Departures from the smooth Hubble flow. Thousands of such measurements blend into a velocity field. If an invisible tugboat beyond the horizon pulls on large scales, the downstream drift should rise above normal. If it doesn't, Lambda Cold Dark Matter remains the right chart for these waters. Watch the riverbank. If the leaves all lean the same way, the current is doing something unusual. Radio astronomy stages its own test. The Square Kilometer Array will anchor exquisitely stable pulsar beacons for timing, while pulsar timing arrays listen for a nanohertz gravitational wave background, the baseline where a network of cosmic strings might sing. Sharp bursts from cusps, a steady hiss from loops. If there's no background or the spectral shape is wrong, the string's tension shrinks into a tight corner. If the hum appears with the right contour, a new branch of the investigation opens, like a seismograph finally tracing stress along a fault. LISA, the space-based laser interferometer, tunes in at millihertz home to massive black hole binaries and some string scenarios. A matching spectral signature in both pulsar timing arrays and LISA would be heavy evidence, the equivalent of two independent witnesses describing the same handwriting. Right now the checks line up along common sightlines. CMB S4 and Lightbird probe the ancient light in temperature and polarization, chasing B-mode curls and the proper E-mode around any possible rings. Rubin, Euclid, and Roman map weak lensing and three-dimensional distances along those paths, revealing voids, knots, and standard rulers like stakes and tape on a surveyor's plot. SKA the timing arrays, and LISA listen for a background in gravity waves, searching for the telltale timbre of strings and other rare early universe events. One lock, many keys. They either all turn or they don't. What matters isn't the beauty of a single plot, but the interlock. Temperature sketches a contour. Polarization stamps the epoch like a seal beside a signature. The catalogs along the same direction confirm mass or its absence, the terrain under your hand. Radio hears the right background, a low rumble that proves the machinery is running. Only a chorus of matches elevates a hint into evidence. And we always go back to the places that hurt. We scrub the window with different cleaners, switch sky masks, compare frequencies. If the smudge stays put after every shake of the table, it gets stronger. If it vanishes, it was handsome noise. The Wilkinson microwave probe and Planck taught that lesson well. Early rings looked enticing, then dissolved under stricter cleaning. The next generation must pass an even harder exam. The decisive check remains simple to state, even if it's hard to earn. If a circle is real, E-mode polarization should wrap its edge by the book. If cooling was caused by a void, the same line of sight shows a density drop in optical and infrared catalogs. And weak lensing pulls galaxy shapes outward. If cosmic strings are singing, the spectra of the gravitational wave background agree between the timing arrays and LISA. We walk from temperature to polarization, from shapes to speeds, from optics to radio. The verdict at the end is just yes or no, but that yes has to arrive in several channels at once. Only then does what lies beyond stop being a metaphor and become a measurement. We care less about what's already etched on the maps and more about what refuses to appear. There's no ring in temperature with the textbook E mode wrapped around its rim that survives mask swaps and frequency cuts. No linear seam that shows up both in weak lensing shear and in the right kind of radio hum. No large coordinated bulk flow of clusters. In a courtroom with the jury speaking in whispers, the quiet verdict points to the simplest story: Lambda Cold Dark Matter, one continuous fabric beyond the horizon, rather than a patchwork. Only interlocks can overturn that, not lonely hints. Think of it as a braided rope, strong B modes that match across new CMB maps, and truly independent instruments. Background imaging of cosmic extragalactic polarization, and the Keck array, or a ring plus E mode that keeps its shape no matter how you re-clean the data. Until a braid holds under tension, we keep the working picture and keep watching. From the Wilkinson microwave probe to Planck, from optical and infrared catalogs to late-time matter maps and Type 1a supernovae, the anomalies haven't vanished, but they've grown quieter as the cleaning improved. The southern cold spot is still on the wall, yet once you scrub the dust better, the stain fades. A foreground void can cool part of the patch, and the rest looks like a rare toss of the cosmic coin. Hints of alignment in the biggest patterns dim when you change masks and methods. Reports of a dark flow lose their punch when stacked over hundreds of clusters. Annoying details, yes. Plot twists, no. The outside fingerprints are undeniably elegant. Circles from colliding bubbles, straight seams from cosmic strings, single cells from textures, beautiful silhouettes behind frosted glass. But one channel is only a shadow. We need a footprint. Temperature has to say what polarization says. Optical and infrared counts, along the same line, must show the same underdensity. Weak lensing has to tug galaxy shapes the same way. Radio has to sing the same gravitational wave timbre. Until those pieces lock, traces from beyond remain a possibility, not a conclusion. To stay oriented, picture two rails rather than a checklist. On the rail that's already anchored by data, the ancient light is nearly uniform. The 1 degree acoustic scale sits where it should, and the geometry reads close to flat. Independent standard rulers and Type 1a supernovae trace the same expansion history. It's like surveying a foggy field with yardsticks and finding that the stakes line up with the plumb line. On the rail that could flip the story, a durable temperature ring with the correct E mode that survives every frequency and mask change would matter. And so would a strong large-angle B signal that different teams and instruments agree on. Not just one experiment singing solo. That's the red thread that refuses to wash out, the motif you still hear when you step into the next room. Stack all the layers today, and the simple picture wins by breadth of agreement. Early satellites laid the foundation. Newer missions sharpened the edges. Late-time surveys haven't found a hidden tugboat hauling the visible volume. Voids and knots explain local drifts just fine. Even the cold spot doesn't demand new physics, at least at today's noise levels. And sky cuts. It's a house held up by many beams rather than one showy arch. This isn't a life sentence. It's a working hypothesis. And we say out loud what holds it up. The 1 degree geometry, the near flatness, the concordance between temperature, polarization, and lensing maps. Distances from baryon acoustic oscillations, Type 1a supernovae from the late 1990s. Upper limits from background imaging of cosmic extragalactic polarization and the Keck array. Many compasses, same North Lambda Cold Dark Matter. What would change our minds is a set of signatures that click together like a vault with several keys, a ring that survives harsher cleaning, and an E mode that hugs its edge by the book. A straight seam backed by weak lensing shear, and the right radio spectrum, large B modes that different maps and instruments agree on. If that arrives and lives through the next round of checks, we'll rewrite the blueprint. For now, the most plausible answer is plain. Beyond the horizon, the same cloth continues. The same rules of growth apply. and the same ancient glow keeps shining just farther than we can see. We keep our eyes on the maps and our ears on the hum, waiting for a new signal that won't wash away. Today's model isn't a headline, it's stability. And in science, a steady clock often tells you more than a drum roll. Imagine we switch off every star and drain away the gas. What remains on the screen is an ancient microwave glow, about 3 kelvins, almost smooth, with fine wrinkles, like sleep creases on a sheet. Those creases carry a history. If the world beyond our window is more of the same, the traces will be quiet and familiar. If it is different, shadows should appear that repeat across independent checks, the way a watermark reveals itself no matter which light you shine through the paper. We lean on what time has already tested. In 1992, CMB first revealed the pattern of tiny unevenness. In 2003, the Wilkinson microwave probe drew the map in sharper strokes. In 2013, and again in 2018, Planck cleaned it further and tightened the error bars. The loudest note on that score sits near 1 degree on the sky, an acoustic peak that points to a nearly flat geometry. Late-time measurements echo the same refrain. Type 1a, supernovae mark, accelerated expansion, baryon acoustic oscillations, lay down standard rulers for distance. Weak gravitational lensing sketches the mass in relief, and peculiar velocity fields explain local drifts with ordinary knots and voids. Stack those layers, and the working picture that holds together is Lambda Cold Dark Matter. We are not locking the door against the unusual. Hints exist, but they've grown quieter under better cleaning. The southern cold spot toward Eridanus stands out in temperature. A line of sight void can cool part of it, and the remainder looks like a rare roll of the cosmic dice. Circles from early bubble collisions were hunted in the Wilkinson microwave probe maps. Candidates appeared, then faded when Planck took over, and the required E-mode polarization along the rims never showed. Straight seams like those from cosmic strings have been chased too. Without a matching weak lensing signal along the same line and the right radio background, a line on a map is just a penciled crease. Careful masks and dust models leave less room for fireworks, more for craft. If a ring truly exists, the correct E-mode should hug its edge, like frost on glass. If the temperature cools because a void sits along the path, the same sightline in optical and infrared catalogs must show a dip in galaxy counts, and weak lensing should pull shapes outward, as if a breeze laid the grass one way. If strings are singing, a linear temperature seam should arrive with nearly undistorted double images where needed, and a gravitational wave background whose spectrum agrees in pulsar timing arrays. One channel alone is a shadow on the wall. Evidence is the shadow and the object casting it, aligned across multiple lamps. At this point, many expect a grand overturn, but quiet can be a result. The ancient light carries neat acoustic peaks. The late-time maps return the same distances and the same geometry. Polarization delivers the E-mode that confirms how structures began to grow. Upper limits on large-angle B modes squeeze the loudest early acceleration stories without breaking the mechanism that seeds structure. Different teams, different instruments, same shape to the melody. That is what reliability feels like. The next experiments tighten the screws. Fresh temperature and polarization maps of the ancient light must reaffirm the spectral tilt and the near Gaussian nature of the wrinkles. If rings emerge, they have to arrive arm in arm with the right E-mode. Deeper weak lensing surveys will thicken our three-dimensional mass maps. If a void explains a cooling, its outline will not hide. The radio band will keep shrinking the space for exotic sources of the gravitational wave background. This isn't a hunt for marvels, so much as a lab rerun with stricter controls and brighter lamps. For now, the most useful, most honest forecast is Lambda Cold Dark Matter, a nearly flat space. Quantum seeds for the first irregularities, filaments and clusters growing under gravity. No mandatory surprises beyond the edge of our window. That doesn't mean forever. It means best read today, from the best and broadest data. If the world beyond the horizon is different, the signatures will braid together and survive changes in frequency, sky masks, and instruments. When that happens, it won't be one pretty silhouette. It will be a story that repeats in temperature, in polarization, and in the late-time maps of matter. The same line written in three hands,